Hello, everyone. Started. Okay. All right. So today we are online. All right. We're going to get started. I'm going to share I'm sharing the screen, so you should be seeing the bright space here. Um, I remind you that exam one is Monday. Okay. So please don't forget. Um, it's in class. Remember, it's closed notes. It'll be like a Word document that you download from Brightspace, and then you have to answer the questions in class, and then you submit it back. Um, yeah, so that's so please don't forget the exam is on Monday. Today we are going to finish up the topic of the perceptron. So I just have a few ideas sorry, my notes. Put them over here. All right, so we're going to finish up some of the ideas of the perceptron, um, and that will be it as far as the perceptron, and then you just have the homework assignment. So I will go back to Anaconda. I've done some of the math, some of the derivation of where everything comes from. And then today I just want to highlight some of the ideas from Monday in Python with NumPy, and then essentially I don't think this will take the whole time period, so I'll give you some time if you want to ask some questions, etc. So this homework assignment, I think is still due. You still have about 2 weeks to complete. I know some of you have already completed it, but yeah. So this is the last day for the perception. All right. Before we begin, are there any questions?
For this lecture, right now I'm on my desktop, which I don't
I
think has
don't
Python
see
set
any
up.
questions.
Oh,
All right. So let's go ahead then. So I'm going to start Anaconda. I'm going to click on all Anaconda. I'm going to go to the Anaconda prompt. So you should be seeing the Anaconda
I
prompt
believe someone
now.
was asking you a question.
Okay. DIR.
hi. Oh, can you hear me?
Okay. So this is CLS. Okay. I'm going to CD into the desktop. DIR. And I'm going to CD into ITS 365. 365. Oh, there it is. 2025. 2025 spring. Okay. So we're here. And then I think we've done in-class perceptron. So that should be the script. Iris, KNN, tensors, bytes. Okay. And there's some questions. Oh, all right. So can you guys hear me? I'm sorry.
It was Jake. Jake
You
wanted to
guys
ask a
can't hear
question.
me? I can hear them. We can hear you. Okay. So some of you can hear me. I can hear
Can you
them.
hear us?
We asked a few questions, but I don't think you could hear us. Yeah, I can't hear anyone. So maybe it's did I mute it maybe? Give me a second here. Well, according to this, can you speak now maybe?
Can you
Hello?
hear me?
Yes, I can hear you now. Sorry, I must have had it muted. Go ahead.
Okay, cool. I mean, I guess my question's kind of outdated now because I was going to say, are we going to be doing work in Python and Anaconda? Because my desktop isn't set up for that. I guess we are, though.
Yeah, we are. I'll record the video and you can follow it later.
Oh, okay, I appreciate it. Thank you.
Yeah, no problem. Okay, so we are recording. Yes. All right. So let's continue. All right, so I have the script here. I'm gonna pick up with the in-class Perceptron. I'm gonna pick up on that one. And there's some kind of yeah, please mute your microphones if you can, just so that there is no noise in the background. All right, so let's open up the environment. So Conda environment list. Okay, and it should be so pi 38. I think that one gave us trouble. So pi,
Yes,
yeah, so
37.
yeah, so pi 37. So I need to get rid of that one. Let me actually get rid of that because I keep always forgetting. Okay, very slow here. Oh, come on.
Oh, just curious question about the
Yeah, go
exam.
ahead.
How many questions are we expecting in total?
It's gonna have 10 questions. So it can be any type of question from essay to um write some code, explain, you know, it could be anything. But they're not multiple choice, or they're kind of like essay type. And if it's code, it's going to be less than 20 lines of code. So it's going to be 20 lines of code or less.
And you said we get a cheat sheet, right?
Right. It is closed notes, but you should have you're allowed a cheat sheet, just like one of these 8.5 by 11, and you can write whatever you want on it.
On both
Is
sides too.
Sure, on both sides is fine.
Okay.
okay.
What's
So
the date
one
of the
page,
exam?
double-sided.
So what's that?
It was
Um,
one page, double-sided, 8 by 11.
Yeah, you can, one of these 8.5 by 11, and you can write
Okay.
on both sides whatever you want. You can use a magnifying glass if you want.
Okay. All right.
Yeah, not a problem. I just want you guys to study, to be honest. All right,
Yeah.
so
oh, I'm sorry.
yeah, go ahead. Yeah, go ahead.
When exactly next week is the exam? Is it Thursday or
We
Wednesday?
meet Mondays and Wednesdays, and then the exam is on Monday.
Oh, okay, okay.
Yep. Sorry, I don't know
No, that's
why.
fine. You probably said this a while ago, and I just
Yeah, yeah. Okay. Sorry, my internet, I don't know, it's slow, so I could never get what I needed. I think it's GitHub that is slow. All right. Yeah, I think GitHub is the thing. All right, I'll do it some other time. So let's activate the environment conda activate. And it's going to be pi 37, 37, 2025, ITS 3065. All right, so pi 37, 2025, ITS. All right, so that's our environment. ELS, EIR. All right, so I'm going to start the Jupyter notebook now. And like I said, today we had already done the Perceptron. So the Perceptron was already done. I'm kind of just going over some additional ideas of it. And that's essentially it. So I'm going to click on in-class Perceptron, which should be the one. Okay. Now it started functioning. Great. All right. So, what is the first thing that I'm going to do? So the first thing is, if you remember, you have to go back to the notes on Monday. But one of the things that I said is that we have a function and that function has a graph, right? So that's kind of what I want to show you today is that we can have these these functions that we create actually have a shape in the system. So for instance, here, I'm going to have a function such as, and I'm going to define this. Let's just see. So y equal, m times x plus b. Okay. So I can create then a plot. So I'm going to create a plot. Mhm. Sorry, my internet is just really slow and all this is. Okay. Let me see if it's the computer. I'm going to try this on my other computer. Yeah, this must be my Mac. Okay, so this one's a little bit faster. All right, so first thing I want to do is just create a simple graph. Okay, let's take a look. Machine Learning Foundations. So this is the perceptron with plots. And I have a little plot here. So I'm going to try to create, just a little plot of information. Okay, so we're going to need for this a library such as matplotlib. So that's the common library, which we should have already in the script here. So let me restart this one. I'm going to clear the kernel, restart and clear the kernel. Okay. All right, then I'm going to run that. I have the libraries now. And essentially what I need is some data for plotting. This should be helpful. Control copy. Okay. this over here, Control V. And so we need to set up two lists of data so that we can plot something. So I'm going to create here X axis, I'm going to call it, and then this is going to be Y axis. Okay. And so what happens is, if you remember when I was doing things on Monday, I was showing you, okay, we have a function and we can, think of it as a line separating data, right? And we're going to change the W's and the biases, and that will essentially change the shape of the graph. So I'm going to try to do that here. Okay, I'm going to need two things. I'm going to need the x-axis data, which is just some numbers that I can have in here. So I'm going to do for I in range, and then I'm going to say from, let's say, -3 to +3, right? And I'm going to print this out. Okay, so if I run that one, okay. Oh yeah, sorry. There we go. There we go. So I have some numbers from 3 to 2, right? And this is the X data value. So and now I want to be able to plot some values related to X. So those are going to be my Y axis values. But these Y axis values are going to depend on some function that I'm going to define. So I'm going to do Y axis. Okay. And it's going to be essentially this function over here that I'm going to try to set up. So I can do something like Y-axis. Again, another list comprehension. Say J, for J in range. And this is, or actually this is not in range. This is going to be the list of values in X-axis. See that? So if I list this right now, it should be the exact same list. There we go. So they're both the same. But now I'm going to change these essentially based on some function that I want to define. But I have data right now. So let's go ahead and try to plot this one. Let's see what happens. And as you can see, I can create a graph, which is what I was talking about. Any questions so far? So there is no actual, there never is a graph. The graph does not exist. What exists is the data, x-axis and y-axis, right? The data in there. And this minus 3 here corresponds to this -3, this -2 corresponds to that one, and so on. So there is some kind of an inherent relationship that they have, and that's what the graph shows you, okay? So now I'm going to modify these values. So I create some kind of a function, such as this one, and I'm going to say what? I was going to say a line, right? So it's a function for a line, and this will take some value. Let's call it K. And so now I'm going to say 1, 2, 3, 4. So this is going to return a value, and it's just going to be the equation. So I need to have a value for M, of course. So M times K plus B. You see that? So that's essentially something I need to have. So let's just say, oh, sorry, M, which remember M corresponds to the weight. So actually, to be more consistent, I'm going to change it to weight. And this one over here is going to be the bias, just like that. Okay, so now what I want to do is this J, I want to modify it so that the relationship between x-axis and y-axis values is different, and it's governed by this equation that I'm creating here. Okay, So I'm going to say something like, I need to plug in that J in that function. Actually, to keep things simple, I'm just going to add these values in the code itself and modify them there. So this is just a simple example. So I'm just going to say that W is, something like 3 for now. And the bias is going to be, let's say, 2. Okay, so I just have those two values, pick them at random. Okay, so I'm going to go ahead and run this one. Okay, got that one, got my X. Now these Y-axis values, I'll need to change. But for now, I can render a graph that looks like that. So now what I want to do is I want to plug that J in this function align. See? So that the function transforms each value. The input is J, and the resulting y-axis value should change. So now look at these values down here. They're going to be governed by this equation. And that's a none. Why is that a none? J came in here. Oh, no. Okay. Yeah, that makes sense. So no return. So return. Okay. I need to obviously return something. I wasn't returning anything. So now let's do it again. Okay. There you go. So you guys can see, okay, I had some X values. I have my Y, my function. The values that you remember with the perceptron, you are learning these values for whatever task you want. But I'm just trying to show you how these control this idea of a graph. So now that I have data in X and Y axis, let's plot it and see what happens. So you can see it's actually still a straight line, but it's different. So what I should have done is I'm going to have two of these y-axes, the before and after. So I'm going to say here, control copy, right? So they are lines, of course. This is just going to be J. So we're going to call this before. I call this before. And then we're going to call this one J after. Okay, so that's essentially what I'm doing. So now I can create two plots. So I'm going to go, that one is, why is that? Oh, let me refresh all this. Okay, I'm going to run it again. Yeah, this is, okay. Got my function for a line, my X axis, I'm iterating through the values in X. Axis. Got it. I didn't change that. Right. There you go. See that now they match. And then the other set of values, because it's going through the function, and same error. Running it, and there you go. So they are different. So now I'm going to proceed to plot both of these. This is going to be, copy this. X axis is the same, but Y axis is going to be before. Okay. Run that one, gives me that line. Okay. And then I'm going to do the other one. This is going to be y-axis after that one. And as you can see, what has changed, the relationship is kind of the same, but what has changed is the, like, on the x-axis, it goes from -3 to 2, that's the same. But on the y-axis, it goes here and before from -3 to 2. But in this one, it goes from -6 to 8. So it's been like shifted somehow. Do you guys see that? So that's essentially what has happened here is the graph has moved. So we can do other things, like now we can try to play with these values. So I'm gonna try to play, and I should have put these on the same graph actually. It would have looked nicer. Um, but I don't have the exact code for that right now. All right, so now let's play with these. I'm gonna change 3 to -3, for instance, if you notice. So I'm just gonna change that weight and see what happens. Okay, the values have changed now like that. Before is still this straight line like that. And if you look, the line has changed, right? So now so it's basically like I'm playing with this line, right? I changed the values, the W's, the weights and the biases of the equation. I made the weight, um the slope of the function negative, and you can see that essentially I did sort of like I moved it. Like if I have a pen here, I have a pen actually. So I did this and I was able to rotate it. And that's the power of changing the weights, that you can see that things can change essentially. Let's try another value. Let's say that weight is 0, for instance, and let's see what happens. I'm going to hit run. Got some values there before, got some values after. So there's the line. Now, if the weights are 0, look at what happens. It just becomes a straight line. Okay? So that's essentially the power of this. Another thing we could do is, let's say, you know, let's do, what if we gave it like 38 in the slope over there, just higher value. Okay, so you can see the values there. That's the normal line. And that's kind of, it's just at a higher position, basically. Okay. Um,
So is that like the magnitude just increasing? Like you put 38 and the
I'm
magnitude?
I'm I'm changing the position of the line. So it's what's changing
Yeah.
is here. It's not
Yeah.
the magnitude of it necessarily, but
Okay.
because this line is infinite actually. So this line depends on, it's not in that regard. Like you're thinking of like the length of a vector, but this is an
Yeah,
infinite
maybe.
line that could go from minus infinity to plus infinity, and I'm just showing the relationship of it. And what's important here is to understand that I can control that line just by changing the parameters of W and B. Do you see that?
Okay, yeah.
And so that's what we're doing in a neural network, essentially. You're always changing the weights and the biases to fit your problem, but you are essentially moving this in, this graph in various directions. So like I did before with let's do another one. What if I do like 0.01 as a weight, right? And so we run that. See the values there. It's always a straight line. You can see that it just moves in this axis a little bit. But the slope of it is really important, which is something we can change, -3. And of course, as we start adding more values, it can become even more complex. So if I had, in this case, I only have one value though, K. But if I had another value and a W, and so you have more control of how that graph moves around. Okay, does this make sense, guys? So the point of this exercise is just to see, remember that in any machine learning algorithm, we're always, this is the input X. We need to predict some value. We need to figure out the parameters W and B. These parameters are what we're training on and learning. And there's essentially, you know, we don't have graphs that exist. Instead, we just have the equation that governs the relationship between the input data and the output data. And things are going to look, have a specific shape. We can try other functions. So these are all linear, by the way. So these are always going to be a straight line. But we can change this to be something like the following. So I'm going to take y equal w. So somebody has a question. Jake, go ahead, please.
Uh, yeah, about what you just said a few seconds ago. So I just want to make sure I'm understanding it right. But the point of
Yeah.
these kinds of algorithmic equations
Yes.
is to use the m, which I understand as our slope and representative of our weights,
Mhm.
to use that and the base, which I believe is the bias,
The bias, yes.
to use those to predict y. Is that correct?
Yeah, that's right. You are
Earlier?
predicting white. Exactly. So in this example, I gave it K, which is the input, and given this W and this B, it predicts Y. Exactly.
Okay,
Exactly.
okay.
Exactly. This is the something called linear regression. So for instance, if you give me square footage of a house, and we'll see this later, but we're just talking about the perceptron now. But if I give you, square footage and I learn these parameters, then I can maybe predict the price of the house. Okay, so at that square footage, that house should cost in this market so much. Do you see that? But the way that we change it is this value that we get here in y, then we made it through an activation function in the perceptron, either +1 or -1. Do you see that? So we just further limit it to two options
Sort of, I think.
because it's a classification problem, essentially. But the thing is, this machine, just think of it, it's a machine that produces numbers, right? You saw it here. You give it these x's and you get these values. And if I change those parameters, I get another set of values. So in the end, what you want to do is you're always predicting and comparing to your real values. The nice thing is you don't have to say, okay, as I did here, I kind of like with an if statement said, okay, W is -3 and B is 2. Instead, we have a general machine that can be applied to many, many, many problems. You don't have to set these values like with an if statement. Instead, you just give it data. So you give it, for instance, for every K that you give it the real Y. And then the machine predicts, as it's learning, a Y called Y pred, and it then just compares and it tries the different weights and biases until what? Until that predicted Y is as close as possible to the real Y, which is called a minimizing of the error.
Is
You
this how
see
you
that?
train the
This is how you train. Yeah, exactly.
so just to
Yeah, go
re-say
ahead. Yeah.
what you just said earlier, so for every K that you give your algorithm, you also
Yes.
give it a corresponding Y,
A
and the
real
hope
Y. Yeah.
is after analyzing the link between these over a period of time, it'll eventually just be able to predict the Y when given a K.
That's right. It learns to do that. And the way that it learns to do that is what it's trying to learn is this W and B, right? Because initially it's random. But all neural networks, what they try to do is they try to learn what these parameters should be. And the way that it does it is because it's got the real one, it can compare it to the predicted one. And it's like, okay, the housing price with these parameters is 300,000. That's what I predict. But actually, it was 200,000. So then the difference is 100,000. You need to decrease that difference, or also called error, until it's close to zero. And you know that the house is 200 and it predicts that it should cost 201,000. Do you see that? So you minimize that error. And that's what we were doing in the for loop of the perceptron when we looked at it last week.
Okay,
Make sense?
I think so.
Yeah, so exactly. So this function won't change. It's just going to have more parameters. We're going to add more things to it. But this is always the way it works. You have a k, you multiply times some parameters. Here I'm saying what they are. And they're not right because I don't even have a defined problem. But over time, they're going to be learned. Yes, exactly. All right, another example I want to do is, if you remember on Monday, I said that there's actually two functions. The other function is the one that calculates the error. And I said that that one is y minus, and let's call this y hat because I can't draw the little symbol, the caret, but it's just the predict, or actually, let's to even simplify it, it's y real versus y pred. And you're trying to minimize this with maybe like sometimes you have a square here or something like that. But let's just keep it simple. There, you're trying to minimize the error, right? And then squaring is this, like that. So to get rid of the negative effect. And we did this on the board on Monday. So if you look at it, this y minus y pred, when you take the difference of it, just becomes diff. And then it's just one parameter squared. You see that? One parameter squared. So it's equivalent to what you're seeing here, w squared, some value, right? So what I want to show you guys again is that this has that bowl shape that I was talking about. So I'm going to use the same k as an example, but it's a different function now. Okay, the function is now, instead of being remember this, there's two main functions in neural networks, right? So the first function, one is the inference function. Don't forget that one. And then the next function is the second important function is the loss function, or called the objective function. And it's usually going to be a combination of y real minus y pred, and you square this one to get rid of the negative. But if you look closely, y real and y pred just become, oh, that should be a minus, sorry. Should be a minus. Y real and y pred just become a value, which could be called a difference. And then that still is squared, just like that. So if you notice, then you plug in a value in there and square it. So I've kind of written this down here just to show you an example of what that looks like. Everyone with me? So we're going to plot, just like we plotted the line here. Now I'm going to want to plot this one. Okay, let's go ahead and do that. So new function here. Okay, added it. See, I've got these values here. Now I'm going to do x-axis. This is just the same. But this one goes through the function, right? So this one went through the A-line function, which is now just squaring the value. So let's take a look at what it looks like. So this is, that's the old data. And now let's look at, do you see that, guys? Do you see how it's a bowl shape? I know it looks like, it's because it doesn't have that many, it's missing like the +3 here. So what we can do to improve this even further is I'm going to do -30 to +30, right? So I'm going to do that. Oh, I'm printing it, I guess. Yeah, let's not print. All right. Done. And this one, let's not print it. That's too many values. And let's not print this one either. Okay, that's the line as before. But now, if you look, it is a very nice little bowl-shaped curve. So this is one thing that these things are going to change a little. They get more complex. But in essence, the key idea remains. there are, as I've said several times in neural networks, two functions, two equations, if you want to call them that. One is the inference function. It looks like a line in its simplest form. And then there's the second one called the loss function. And this one has this property of capturing the relationship between the error on this side over here and um, the W's on this other side. So if you remember, like the intuition is if my W here, my weight is minus 20, the loss function tells me that my cost is around 400. But what I want to do is get to where my cost is 0, right? So it would be around here. So I need to descend. And that's why we talked about gradient descent. And we established that we want to do that. That's our goal. But there's a technique in math that in 1957, they said, okay, we can use this technique called the partial derivative of W in terms of this function, and that will tell me which direction I should go in. And that's it. That's essentially what I derived on Monday, but I just wanted to use Python here to show you that these equations have basically map our relationship, remember, between x-axis data and y-axis data. Or you can have more axes that holds mathematically, but visually we can only look at things in 2 or 3 dimensions. So lines or this curve. Okay. Any questions on that idea, guys?
I'll just follow up. So
Yeah,
the
please.
error on the left side and then the weights on the right all converge into what, 0, which is your ideal.
Right. So this side here
You
should
want,
say
0
error.
error and
This should
prediction.
say error. Yeah, this should say error. And
And that's how
this,
like
go
the
ahead.
accuracy of the model is dependent on these two meeting at about with 0 or
That's right, because on this side over here, on the x-axis, what you're controlling is the W, right? So we went over that equation because, so think about it, right? So here, I'm saying that y real, y pred. Y real is just a value. Y pred is actually a function that depends on W. So if you look at it, y pred is actually what? W times the X input plus the bias, right? And so really you kind of do this for the W and the bias. But so that's why it's called a partial derivative, because you take the derivative just for that particular parameter at that point in time. And so in this case, we do it for W. And so that's really the Y pred doesn't matter because it depends on W. And that's the thing that we're focusing on. So that's why in the plot, really the value that goes here in X is the W, and the value that goes here is just the error, because that's what this function captures, right? So the function, these squared is just calculating that error. And so that's what's going to be on the y-axis, and your goal is to minimize that. And so you can move the W around, left, right, but essentially when it hits this point where my mouse is, if you can see that for this example, is the error. Yes. Other question. Go ahead, please.
Yeah. So I know we've been going over this for the past like 2 lectures, but I'm still kind of caught up in. So in the grand scheme of everything, what exactly do these graphs mean in comparison to the models? Is it like at the end of all of these calculations and these graphs, we'll be able to visualize the accuracy of our model, like how close to or how many errors it like has?
So the graph calculates, it's not at the end, I would say. It's actually every iteration from random weights to final product. So what is happening is, a better analogy to what you're saying is, at the beginning of training, your weight might be here. Do you see where my mouse is?
Yes.
Okay. And as you continue to train, if you're using the perceptron rule or the techniques of stochastic gradient descent, this is happening. Do you see that? The mouse
So
is going down and it's going to stop here. But what, that is equivalent if this is happening here, that means that the W value is going, do you see how it's going to the right?
mm-hmm.
And if let's say that it went too far to 10 and it's now at this point, it's gonna know, oh, okay, wait a minute. I need to start going down. So now it's gonna do this. You see that? Until eventually it should stop at this point because that is the lowest on the error. So that's what this, intuitively, this is what happened visually, but there is no visual. Like the neural network doesn't look at this graph and says, oh, okay, I'm gonna go, that's what we do as humans. What the algorithm does is it looks at this, right? So it's got this process of, it's got X, it's got these parameters, it predicts Y pred, it takes Y real minus Y pred, squares it, takes the difference of that. And its goal is to always minimize that. And every iteration, in the equivalent of us looking at it and knowing that we go right, is that every iteration, it looks at where it is and it says, okay, I'm governed by this function. I am currently W0. I'm going to perform this math operation called the partial derivative of my function. And that's going to tell me if I should go left or right. Do you see what I'm saying?
I think so. So these algorithms are essentially their entire goal is to move W as close as physically possible to zero.
That's right, exactly. And the beauty of this is that, like, the magic is that this equation here, for instance,
Mm-hmm.
has this analogy of this behavior because it's exactly what's happening. It's just that the algorithm does not create a graph, look at it, and then make a decision. It just does it mathematically. But that's what's happening essentially.
Okay, so in that case, and
Yeah,
W is representative of the weights.
that's right. W is literally this value here.
Okay.
That
Oh,
value is the one that you're trying to update. So why? So in this example, I was just doing the graph, but if you remember in the perceptron, I actually there's a step, right, that does W equal W plus or minus some learning rate times, oh, and that should be times here, times Y minus, Y hat, let's say. Do you remember that? So this is what updates. Oh, this should be a W. Do you see that? So you
yeah.
are, with the information that you obtain from the laws, this idea, you update. You can see how, notice what's happening here. Maybe to be more obvious, put a minus in there. So you have the original W and you want a new W. And what do? You either add or subtract something from that W, which is this value is fixed. So you can fix it at either a tiny one, which is probably too tiny. It'll take forever to modify it. Might be better to just do something like that. But this guy here, this tells you if you should, it's going to either become plus or minus, which determines if you add or subtract from W. Get it?
I think so. So the algorithm
Yes.
so it's going to be using the algorithm that you just wrote there to determine whether or not it needs to move the position of, or not move the position of W, but change the value of W to get closer to zero. So it will
That's right.
then use Y minus Y hat, or sorry, Y minus Y underscore hat, or yeah. So it's going to do that, and depending on whether or not it wants to go forward or backwards in terms of value, it will change it from a subtraction to a addition problem.
That's right. And you can see that here. So if your value is, if you're, this is because axis X is the W in question. whether it's W0 or W1 or W3 or W5000, right? Because you're going to have many weights later on. You do it for each one by taking the partial derivative of the function in terms of that specific W. That's something you don't have to do, by the way, manually. It's done through the library. That's why we need a library, because you couldn't do that for 7 billion of these. But essentially, that's what is happening. Let's say this is W3. It is minus 20. You move it. It needs to be minus 20 plus 0.05, let's say. So it moves a little bit, and then it just keeps moving, and it's gonna know where to stop because of the function that always tells it wherever the W is here, it can tell you what the error is here. Do you see that?
I think so. So the x-axis is weights. What is the y-axis again? Is that the learning rate?
The y-axis is the error.
Ah, I see.
It's the error. So that's the thing that you need to figure out. So for instance, here, remember, this is the error essentially. See that? So that's what the equation is. So here, I guess I didn't write it yet. Error, like that.
Hmm.
Does that make sense? So this is actually the complete function, right? So the error, the second function, is equal to the y real minus the y pred squared, where the y real is just a number. Y pred is this equation over here, where you can't change x because that's your data, but you can change w and b because those are the parameters that you're playing with. And you're optimizing them or updating them every time, every iteration, until your goal is to arrive at this 0 down here. Do you see that?
Yeah, I think I do.
Okay, great. Yeah, good questions. Any other Oh, so Jake Delso has a question?
Yeah, no, that was me.
Yeah.
Yeah, you could take it off. Yeah.
Okay. All right, great questions. Any other questions, guys?
No, I'd say that was pretty good explaining it in more detail because I understand how now is actually its process of reducing errors and using weights to
Mhm.
achieve. So
Yeah. So exactly, good. So yeah, that's why I wanted to do this. So yeah, and that's, believe it or not, I mean, this is it, right? So this is the key concept that you need to understand. Neural networks will just have, unfortunately, they're not going to have this perfect behavior of one bowl shape. Instead, think of them more like a mountain range of valleys and peaks. And so I think I was talking about that on Monday. Because of the nature of how they are, they're much more complex functions. Just the shape becomes a little bit more complex, but the idea is exactly the same. Wherever you are with that weight, figure out gradient descent, go down, and hopefully, if you're lucky, you'll get to a global minimum. Right. And so that's the idea. So that's why I wanted to do this example before we kind of like circled back to the perceptron. I just wanted to show to you that you can plot these graphs and play with them, and see that these shapes have actual interpretation. Again, it's not that the model looks at this picture, right? Because it doesn't need to. It just needs to look at the values of the equations and it gets the exact same information. All right, so we did that example, which was the graph. Right, and I think that was it for that one. I guess the other thing I wanted to show you is this operation called the dot product. So the dot product is also in your perceptron code, right? So if you remember, here, NP dot. Do you guys see this? And that might throw you off because you're used to seeing. So let me copy this actually. Copy that one. All right, so where can I write? All right, so That's the equation. I'm writing this one down. The line that we just plotted. Y equal mx plus b. I'm going to change this to be, x test. X test. Or actually, that should have been the x. So the first one would have been the weights. And then the bias. Okay, so you can see they have the exact same interpretation. It's just that I'm using this operation called MP dot instead of the times. So you understand probably, that you can do y here equal what I was doing, 3 times, I don't know, 5 plus 2. So that is easy to understand. But in machine learning, we have to use, to be efficient, we have to use two important concepts called parallel computing, and we have to use something called GPUs, right? And most of these come from a company called NVIDIA, which if you've followed, they're worth a lot of money. They are one of the most important processors for machine learning because they allow you to perform operations efficiently through these techniques, which I called tensor operations, which is what you guys did, the 70 or so problems that you did at the beginning of the semester as practice. Those tensor operations are just a subset of an area of math called linear algebra. Now, you don't need to understand everything about linear algebra, but you definitely need to know how to do these operations, right? And so the way that I would describe it is that it is a way to do multiplication, but in a different way, right? So you have this thing called vectors and matrices, okay? So that's what I want to talk about today is just give you an example of this dot product. So let's think of an example where, I can describe something as just being a value. So for instance, I'm going to describe a house as just being square feet. Okay, so square footage. So that translates into being, I don't know, square footage of a house is, say, 1,400 square feet or something like that. That's one single value, right? And that you would call a scalar. It's like a set of just one, okay? Now, a vector is when I want to describe efficiently something, which we've also called the features. I want to describe something with two value or more values, right? You know this, what I call vectors and features. So I'm kind of just going back to that. So in this case, I'm describing the house as square feet, but also, let's say, number of bedrooms and the number of bath bathrooms, let's say, in 2. So you're describing a set of values. So just like before, we were multiplying one value times another value. We can do that in parallel. What I mean by that is, let me do that here. In the equation that is y equal w times x plus b, right? And I'm going to ignore the b just to keep this simpler. So then I'm going to say, okay, y equals 35, I made that up, times square feet, which is 1,400, right? And now I can predict the price. But what happens when I have these 3 values instead of just one value? Well, I could maybe do this operation in sequence. So how would that work? So then I would have to do y1, y2, and that one's going to be like 98 times 3. And then I'm already super tired of this. And so then I do, 224 times 2. Do you see that? So if I was doing this in, say, a CPU, this is just kind of a exaggerated example, but if I'm doing it in the CPU, I have to do this first, then I have to do this second, then I have to do that, and it just takes, forever, basically. It's very slow because it's sequential. The GPU and linear algebra and tensor operations allow you to do this sort of in parallel. And all you have to do is you group these values. So I'm going to group my x's, right, into a vector. So now it's going to be, what is it? 35. No, sorry. The values are actually 1400, 3, and 2. Do you guys see that? And then I have another vector called w. And in there, I group the weights. So it's going to be 35, 98, 24. Okay? And so that's it. So in this dot product or tensor operations, what you do is you kind of think of it in a very simple way as just multiplying all the values, but in one shot. So if this would take 5 seconds, let's say this takes 10 seconds, 10 seconds, 10 seconds. So that would be a total of 30 seconds to perform this operation versus doing this one down here, which only takes 10 seconds. So there's a huge savings in time, and therefore you can train much faster. So you will perform the exact same operation, add them up, etc., but you do it all at once. So that's what the dot product function is doing, that I have over here, the NP dot product. To further illustrate that, though, I want to show you how that would work kind of manually, and then we're going to compare it to the dot product approach. So let me add here. I'm going to create some data, right? So I'm going to create A, and A is going to be, let's say, 2, 4, 6, 3. This example is on the GitHub, by the way, under neural nets and in maths. So then I have 2, 4, 6, 3. Okay. And then I have B, 1, 7, 3, 2. Okay. So I'm going to perform the dot product between these two things. So I'm just going to say result equal NP dot was it NP? I may need to convert that to NumPy. NP dot, yeah. A comma B. All right. And then print res. Right. It doesn't like it. Oh yeah, well, I didn't. So it actually did it. All right, so 54. Okay, great. So you can see that, guys. So I didn't even have to change it into a NumPy array. It just took it and it told me that it was 54. Okay. Now let's look at how this could be done manually. So we're going to write the code for that. So this is more like for loops. So I'm going to do my dot product. Okay. And it takes, once again, A and B. Okay. So what we do now is I'm going to do a list one, let's say. I'm going to do a list comprehension. And I do for I in range, where the range here is going to be the length of one of these. So let's say the length of A, right? So I can grab the index 0, 1, 2, 3 of these. And now I'm going to perform the operation manually. So what I do is I take A, I times B, I. You see that I'm doing it literally manually. And that's equivalent to this idea that I gave you over here of multiplying, the 1400 times 35, the 3 times it's 98, the 2 times it's 24, and then adding them together. So this creates the list. And then this list is going to give me the result. Okay, that should be sum of list 1. Okay, and then I'm going to return res. Okay, so that should work. Run. Okay, now I'm going to just do my dot product. And this will take A, comma, B. And if you notice, it gives me the 54. The 54. Okay, so that's essentially the operation that I was doing, but I wanted you to understand that it's kind of like every corresponding weight with its corresponding X value. Does this make sense? Are there any questions with this idea of the dot product?
Yeah.
Yeah.
So if
Yeah, go ahead.
like let's say on the exam we have to like do like the dot product. Are we gonna have to know how to write it out manually, or can we just do the NP dot and that would be fine?
You can do the NP dot dot. This is just to show you where things are coming from, essentially. Just to kind of give you an idea. And to tie it back in particular to this equation, right? So usually you see this and it makes a lot of sense that, okay, the W times the X is a number and a number, but what happens when they're, a vector, essentially? What is happening there? But you
Right.
understand that this is very convenient, right, to do things like this because you definitely, you don't want to spend, let's say I gave you a homework assignment, you don't want to spend all weekend running this when it could take you less than an hour to running it on a GPU. Do you see what I'm saying?
Yeah.
Yeah. So it's definitely something that is key. We would not have Chat GPT and all those things if we didn't do these operations because it would take 5 years or just to finish one run. It would be impossible, essentially. So parallel computing is pretty important. All right, so today, yeah, so that was really my goal for today. I wanted to go over the graph, the visualization one that we did. So on Monday, so just a recap. On Monday, I went over the perceptron derivation of the learning rule, right? And I showed you guys this idea of taking the partial derivatives, and I showed you how that worked. And we arrive at the learning rule. And you understood that there's two equations, the inference equation and the loss equation. And that's not going to change even when we're training a GPT, right? Or something like that. And then I wanted today to show you the graph so that how functions govern the relationship between data, right? And they change the behavior. And so we saw the little graphs that I did. So the graph for the inference and actually the equivalent graph for the bull shape. So what I'll do now, the last thing I'll do today is really just go over the code, the Perceptron code that we had done from last week, which should be this one, and kind of let you guys, I'll just talk about it again now that you have 2 more lectures in between when you first saw this and now. So I'll go over it again and I'll let you ask all the questions that you want, and that would be it for the perceptron algorithm. Okay, essentially. Make sense? Right? Sounds like it is. So this is the code. So I will delete some of these things given that I don't want to, have it be, complicated. I'm gonna remove this one. Remove that.
Will you be putting this on your GitHub or no?
This Perceptron code should be there already, isn't it? It's already.
Yeah, it is.
So if you go to neural nets Perceptron, and also when I did the homework, I think I linked it. So it's this script here.
Okay, thank you.
Yeah, it's already there. It's been there almost. And this is the one that I did in class last Wednesday. Do you see that? Remember how I said to you guys that even though the scripts are in their corresponding subfolders, I did create a 2025 folder. So the scripts that we do in class, I uploaded here. So we've done 2, KNN and Perceptron. Got it? All right. So next week, after the exam, we'll do something called the Hopfield Network. You'll be excited to know that the gentleman that created that, called John Hopfield, actually won the Nobel Prize in Physics for that algorithm. So you'll see actually a thing, right, that won a Nobel Prize. And that, but it's also a neural network. That's the beautiful thing about all of this, is that even though the perceptron right now seems pretty maybe new and different, once you start in the progression of neural networks, everything is familiar. So the perceptron, Hopfield networks. So perceptron was first, definitely. Then Hopfield networks. Then there's a few in between that I may skip, the Boltzmann machine, but definitely a multi-layer perceptron from scratch, which, as you can see, is just multi-layer. And then from there, we'll look at linear regression, logistic regression, MLP again, and deep learning. And it's all a progression of the same ideas of the perceptron. At some point, our y minus y hat squared may change to another loss function, but essentially the same. All right. So anyway, so today I just want to wrap up with the perceptron here. So I'm going to remove these, and kind of it's a recap. Okay, so I'm going to take that out. Okay. All right, so here we are. So this is the perceptron code as we had it. So we had an activation function, which, if you remember, is just once you get the y value, that y value is going to be forced to be either a 1 or a 0, right? Because this is a classification problem, not a regression problem. That means that just, we just want to say, is it a T or an L, right? You can think of it almost as being a binary thing also. You want to say, is it true or false, given this question that I have, right? And so you can think of it that way. So if I do the activation function, for instance, if I give it a minus or a minus 0.7, it just makes it 0. If I give it a 1.7, it makes it 1. So it's always going to be 0 or a 1. Then we had the actual code to fit our model, which was this. And that, remember, would just give us the weights and the biases. Okay? I'll come back to this one, of course. We started with a data set. I just created some random data, 150 samples with 2 features. For your example, you guys, for the homework, you're doing images that have a size of 16. Remember that. But I'm just using 2 for simplicity. And then these 2 values, I'm creating data that comes from two distributions, two here that have, that have specific characteristics. So I can do the data here, print a shape. I have 150 samples and two features. I can look at the data if I like, and you can see there's a little bit of information there. I can do the Y shape also. There's 150 labels from 0 to 1. So that's why my activation function also matches this. Okay, so we can look at the data there. Then we split the data, which is so that we have one set of data for training and one set of data for testing, right? So 120 samples are going to be given to the inference function that has bad weights, right? But as it's training, those weights need to improve. Once it's trained, we're going to evaluate it on the test set, which has 30 samples. Make sense? So once you do this and you have your fit function over here, you give it the X train, Y train. It trains for a little while in a loop, and essentially it gives you the weights and the biases. It gave me an error here because I didn't load that fit function, but we'll come back to it. Once I have the weights and the biases, you can print them. Then you just invoke a predict function, give it now the test samples, the weights and the biases. And if you notice, it's just going to plug them in its inference function, which I just explained, right? The NP dot, it's the dot product. So it just takes the X vector times the weights plus the biases, and it predicts a value. But this value currently could be a 7, could be a 3, a point. So we want to make sure that it's just either 0 or 1. So it goes into this activation function, which is essentially an if statement, and it'll return here a 0 or a 1. And that's it. Okay? So now the key part is the algorithm of the fit function. Okay, so let's go back to that one. Okay, so it's this one here. So let's go through it line by line. Defining the knob. So if you remember, I wrote this on Monday, and it's in relation to the device that I showed you, but where knobs are the weights and bias. Okay, so those are the parameters there. I initially create the weights because I only have two features. I only need two weights. So for your perceptron with images, right, you have 16 features. So how many weights do you need?
16.
16, exactly. So this will be 16 for your problem, right? It needs to match it exactly. And your bias will be still just 1 because you're still predicting whether it's an L or a T. You're just predicting one value. So the bias always ties to the output, which right now you only know to predict one output neuron, essentially. Okay? So we create the weights and the bias here just as zeros right now, or it could be random, which would probably be better. Notice that I set this learning rate to be 0.01. Just this is the value that you're either adding or subtracting from the weight and the bias. Then I have two for loops, which is pretty common, right? You have a for loop where you just repeat the same thing for a number of times. So in this case, 1,000 times. And then this second for loop is the one that is serving the data to the perceptron, okay? If I simplify the code, I have a lot of comments here, but if you simplify it, you will notice that it's really just like that. And I could actually make, yeah, somebody has a question. Jake, go ahead, please.
Yeah, so a few seconds ago, you said that the learning rate subtracts and adds to the bias, right?
To the bias and the weights, to both.
Oh, okay. So what's the point of, I guess, like subtracting and adding to the bias exactly? Like, are we looking for
The
an optimal
bias
value
is
of the bias?
the bias is another parameter, like the W's.
Right. But like, is there an optimal like number for it to be at? Like how the weights optimally should be at zero?
It's the exact same curve that we had before. You know the curve?
Yeah.
The bias will be on the x-axis and error will be on the y-axis. So you do it for all, including the bias.
Hmm. Okay.
Do you understand?
I think so.
So, yeah, so the bias, so why do we need a bias? The reason why you need a bias, imagine that all your x values are zero. What's going to happen to that function? All those x values that are zero, when they're multiplied times the weights, all the weights are going to cancel out and you're going to end up with zero. Do you see what I'm saying?
Right.
So by having a bias, you have a term that could handle that situation because if all your x's are zero, but at least you have the b that can have a value in there. And you just have to learn it.
Okay.
Yeah, so it's so that's essentially what it is. It's you always have this one term that is not related to an x. It's kind of just independent. And that also needs to be learned. And it's learned in a very similar way, which you can see it here. So I have the weights and I have the bias, and they're all being updated. It's updated, which is what I'm going to stress now, right? So we have here, I'm trying to keep this super clean and simple, right? So I have the xi times the weights plus the bias, which currently in the first iteration is just zeros. That predicts a value linear, right? And that linear value goes into this function, activation function, which if you remember, it just returns 0 or 1. Once we have that, that y pred is going to be compared to y real. Do you see that? That's the difference. Okay. So what I want to do now is I'm going to write this as, see, this loss is not being used. So I'm just going to delete it here. And now I have this update rule. Okay. So let me move this. So all that's happening is, if you look, you get a sample from the training set with the weights and the biases, you perform the dot product, you arrive at the linear, that goes into this activation to convert it into either a 0 or a 1. Then that 0 or a 1 here is compared to the real value. Take the difference of that times the learning rate, and that becomes the update value, the thing that you add or subtract. So then now you go to you have the weights here, the old one. This is going to be the new one, and you just subtract or add, depending on whatever this solves to, into the update, basically. Now, that's it. That's essentially how all neural networks work. You give it the value, you give it the new sample, given the weights and biases it predicts, and then that predicted value is compared to the real one, and then you have a learning rate, right? And that determines the value of update to modify the original weights and biases into the new one. What's a little bit different here so the original Perceptron had something called the Perceptron learning rule. And so the Perceptron learning rules set two things that are peculiar. One of them is that if you notice, I did not square this. You see that? I did not square it. Later on, we will see that it is better going forward to square it. So you might say, why aren't you squaring this right now then if that's the right approach? Well, I'm telling you the story historically of how things have been done. So the very first algorithm was the perceptron, right? So you have to put it in the context of 1957, okay? So they hadn't yet figured out that actually this is going to be better. But perceptron was just that, no squaring. The other thing, and I'll tell you late, well, I've actually already told you why this is. Because on Monday, when I did the derivation, if you remember, we derived it to this, and I showed you why. But essentially, that's one thing. So one difference from our future approaches. This was not squared. The other thing that you'll notice is that the value, all of this, is multiplied times its corresponding x for that weight. So you see that xi. So what you have to understand here is that because this is written in vector form, right? Essentially, this is like looking at it like this. So it's a vector where you have W0 and W1 equal W0, comma, W1 minus, let's say 0.01. So I'm just plugging in the values here. Times X, so X 0, comma, X1. You see that? So it's actually in vector form. So another way that we could have, I guess, written it is W0 equal W0 minus 0.1 times X0. And then W1 equal W1. Oh, this should be a time. So times 0.01 times X1. You see that? And then the bias is, the bias does not have a corresponding X, so it would just be B times 0.01, no B. So this is, if I break it out, that's what it would look. So every X, every W is being updated this way, but because I've written it in vector form, they're actually grouped as vectors, if you see, and that's why I'm able to write it just like this one line of code here. Does that make sense, guys? Any questions on that idea? Okay. Not hearing any questions. All right. So essentially then that's what you have to get used to. The part that's difficult about machine learning is that here you might say, okay, I want to do it this way. Yeah, great. But what if you have 784 X's, which you will. The smallest images you will do later with MNIST are going to be 28 by 28, which is 784. So it would be a vector of 784. It just becomes impractical. And so you have to learn how, this is in one line of code, you can do something that would be 784 lines of code. So to recap, the perceptron rule does not square this, and the perceptron rule for each weight multiplies times its corresponding x, which we will not do later, but this is done in the perceptron rule because this is how, when they did the calculation, it came out like this, right? And that this is how it worked. And I did this, if you go back to the Monday derivation that I did, I wrote down the equations where it turned out that when you did the derivative of the function in terms of W0, then you would get the result as X0. So we did something like the derivative of error in terms of W, let's say 0. And so whenever you took that operation, it came out to be y minus y hat not squared. This in the result, this was not squared. If the equation had given you squared, then we would square it, but it just wasn't. And then this was, however, multiplied times x0. That's how it came out. Then when we did the derivative of the error function in terms of 1, this came out to be y minus y hat. Again, same. I want them to look like times x1. And when we did the derivative of the error function in terms of the bias, that's when it came out a little bit different. And it was y minus y hat, no term here, no times x. And so when we did this, we arrive at every time that you do it in for the perceptron rule, the y's are not squared, the difference, and given a w0, you multiply times the corresponding x0. And so just, it's part of how it came out when they were doing it, manually. The problem is with this approach is the perceptron, although it's kind of like very nice mathematically, when you look at this, it's like, oh, wow, that's pretty. But the problem is the perceptron does have limits, right? So that's why the perceptron was not the solution to everything. And in fact, we need to learn other techniques, the multi-layer perceptron, deep neural networks, etc. But everything is just an improvement on the original set of ideas. Does that make sense, guys? That's essentially it. Any questions? All right, so I'm not hearing any questions. So let's just run this and make sure it runs again. So I'm going to do run activation. Fit. All right, so I ran fit there. Got my data. Gonna train. So this is where it trains. Okay. So let's see the dot is solid, so it means it's thinking. All right, so it finished. So now we can go ahead and print the weight. So this is the thing. That's the thing of value, right? So ChatGPT is just this, but 671 billion of it. All right, so once you have that, and we predict. So there's our predictions. These are our real labels. We measure the performance, and it's 1. And that's it. All right, that concludes. I'll stay for a few minutes to answer any questions that you might have. Otherwise, that concludes our discussion on the first neural network, the perceptron, and then we're just going to move forward from here to other neural nets. Okay, so I will stop the recording. I'll post this later today or tomorrow. And